Soft-hard interfaces are a common occurrence in man-made devices, and frequently, these interfaces are where mechanical failures happen. Living organisms, including the human body, contain many soft-hard interfaces too. However, mechanical failure almost never happens in these natural interfaces. A major challenge in biomimetic design is to create man-made interfaces that perform as well as their natural counterparts. We show how complex geometric designs and multi-material 3D printing can be used to create bio-inspired surfaces that approach the theoretical limit of mechanical performance. We used triply periodic minimal surfaces, collagen-like triple helices, and a random distribution of hard particles to generate interfaces resembling tendon-bone connections. We applied a combination of 3D computational models, multi-material voxel-by-voxel 3D printing, and mechanical testing under shearing tension, as well as fracture tests, to evaluate the performance of different soft-hard interface designs. Our analysis suggests 3 design principles that enable soft-hard interfaces to approach their theoretical limits, including increased contact between soft and hard phases, smooth and compliant transitions between the extremes of softness and hardness, and avoiding strain concentration zones. Implementing these design principles leads to an increase of more than 50% in interface toughness, while moving the failure location away from the transition zone, which is the ultimate goal of these design endeavors. There are many devices whose design could benefit from these principles, including bone implants, soft robots, and foldable electronic devices.